Have you done the homework? What did I ask you? You were to take the two equations for our motor control problem, one voltage equation for the armature circuit, and that involved derivative of the armature current multiplied by the armature inductance, and the second was the mechanical equation, torque equation, and that involved derivative of the angular speed multiplied by the moment of inertia. I wanted you to apply the Laplace transformation to these equations, that is, as one says, take the Laplace transform of both sides and obtain an expression for the Laplace transform of the speed, that is capital omega s, in terms of the Laplace transforms of the applied voltage E A s and the torque T L s, leaving aside the initial condition terms, that is the terms that involve the initial current I A 0 and the initial speed omega 0. We will take care of those initial conditions later. I hope you have done the problem. I am going to do it in a different way. I am going to make use of the concept of the transfer function that we have introduced, and also the concept of the signal flow graph that I had talked about quite some time ago, and the gain formula associated with it. So with this, let us get back to the two equations, but what we will obtain from the equations will be transfer functions, and side by side with the transfer functions we will draw the signal flow graph. So the voltage equation was the applied voltage, and therefore I have its Laplace transform E A of s equals kb times omega s plus R A I A gives rise to R A times I A of s, and L A d I A dt gives rise to S L A, and therefore I will write this as S L A plus R A multiplying I A of s. So this is the Laplace transform version of the voltage equation. Applied voltage transform equal to kb times the speed transform plus this linear factor SLA plus RA times the armature current transform. And as we saw earlier, we can rewrite this equation expressing an output quantity, in this case IA of s, in terms of the two input quantities. Well, we can't quite do it because we have omega s and EA of s. So we will write this as a flow graph equation, taking IA as an output node, omega as an output node, and EA as an input node. And with the nodes we will associate the Laplace transforms of the corresponding variables rather than functions of time, which we had done earlier. In fact, at that time we had only looked at the steady state values, if you remember. So what does the signal flow graph or a part of it look like? I have to put down two nodes, one for IA of s, the other for omega s. So let me put them down, omega s here, IA s here, and I may not write this s now in order to save time, but remember we are dealing with transforms. And then here I have the input node EA of s, and so I have to solve this equation for one of the two quantities, either omega s or IAS, in terms of EA and the other one. Suppose I solve it for IA of s in terms of the other. So I have EA of s minus RA IA of s minus KB omega GS. So I'll write SLA plus RA into IA of s. It's always better to write down things rather than try to do them purely mentally. So this is the equation I have, and now I am going to divide both sides by SLA plus RA to express IA, and therefore IA will be given by EA. There will be an arrow going from EA to IA of s, and that will have a gain of 1 by SLA plus RA, and there will be an arrow from omega to IA of s, and that will have a gain of minus KB divided by SLA plus RA. So these two arrows represent the EMF equation or the voltage equation after the Laplace transformation. Next, let us take a look at the torque equation. So we have KT into IA of s equal to three terms. One is the load torque, so TL of S plus friction, so Kf into omega S, but there is also the moment of inertia term, therefore Kf plus Sj into omega S. Now the first equation I solved for Ia, so the second equation I should solve for omega S, and therefore I will rewrite it as Sj plus Kf into omega S equals Kt Ias minus TL of S, and therefore I will have that part of the signal flow graph, omega S again, Ia of S here. Now the input, other input node is TL of S, and there will be an arrow going from, I am solving for omega, going from Ia to omega S with a gain of Kt divided by Sj plus Kf, and there will be an arrow going from TL to omega S with a gain of minus 1 divided by Sj plus Kf. So these will be the two additional lines or gain relationships, and therefore the full signal flow graph will now look like, combining the two, what will it look like? Draw it. I will now drop that S because I do not want to clutter my diagram. Here is omega, here is Ia, here is Ea, and here is the node TL. Remember, we are going to look upon omega and Ia as non-input nodes, and Ea and TL will be the input nodes. So first I have an arrow going from Ea to Ia, Ea to Ia with a gain of 1 over SLA plus Ra, and there is an arrow going from Ia and from omega to Ia with a gain of minus Kb divided by SLA plus Ra. That is one. The second one is from TL to omega, and I will show it. This is not a crossover, it is not an intersection, this is only to show on the diagram. I have minus 1 by Sj plus Kf, and there is a gain from Ia to omega, which is Kt divided by Sj plus Kf. This is the signal flow graph. And now from this I can write down the desired relationship. Let us say I am interested in the variable omega in terms of Ea and TL. Therefore I have to find out the delta. What was delta? Delta was the discriminant of the set of equations, or by Mason's gain formula it is 1 minus etc etc. So let us do that. We will have delta. There is only one loop here, so delta equal to, there is the one term 1 minus sum of all the loop gains, since there is only one loop, and there is a minus sign, so I will write it first, minus, I will have minus Kb divided by SLA plus Ra into Kt divided by Sj plus Kf, or 1 plus Kb into Kt divided by these two linear factors SLA plus Ra into Sj plus Kf. Okay, this is delta. This is the discriminant which will appear in the denominator. What about the numerator? I want the numerator in the coefficient that multiplies Ea. So I look at the forward path from Ea to omega. The forward path from Ea to omega goes through Ia, and therefore the gain of the forward path is 1 divided by SLA plus Ra into Kt divided by Sj plus Kf. This is the forward path gain. This is multiplied by delta, terms from delta that remain when we consider only loop gains which do not touch the forward path, but the forward path touches the loop, and therefore in the numerator I will have only 1. So I will have just that. This will be the numerator of the multiplier for Ea divided by 1 plus Kb Kt divided by the product of those two factors. This will be the coefficient of Ea. Something similar I have to do for the coefficient of TL. The denominator is the same, and the numerator is what? The forward path from TL to omega, that is a straight one, that is minus 1 divided by Sj plus Kf. The numerator delta is simply 1 as before, and therefore I have simply the denominator which is delta, and therefore I can write down the full expression for the Laplace transform of the speed as omega s equal to, and I will combine the two delta denominator terms, so 1 plus Kb Kt divided by SLA plus RA into Sj plus Kf, that is the denominator. In the numerator I have EA multiplied by one factor, so Kt divided by SLA plus RA into Sj plus Kf into EA minus the torque coefficient is simply 1 divided by Sj plus Kf into torque. One can always check this set of equations for dimensionality to check whether they are dimensionally correct. For example, let us look at the fraction Kb Kt divided by SLA plus RA into Sj plus Kf. Kb is what? Kb is volts per RPM or per radians per second. SLA plus RA is what? RA is resistance, so volt per ampere. So this is given by, you can check whether the dimensionality matches. This whole fraction should turn out to be dimensionless, and one can sort of understand it very quickly because there is a 1 here. Now the number 1 here indicates that it is something dimensionless, therefore this whole expression should be dimensionless. Similarly, in the numerator we will have 2 coefficients which should have the appropriate dimensions. Now at the moment these expressions look fairly messy, and I am going to draw a block diagram later on when we consider feedback, but at the moment we have to work with the expressions as we have them, but we can simplify them a little further by getting rid of this denominator product. And if I do that, then what do I get? And I will now separate the 2 terms EA and TL. So I will get omega equal to, on the one hand I will have Kt divided by SLA plus RA into Sj plus Kf plus Kb Kt. This whole thing multiplies EA minus SLA plus RA multiplying nothing divided by the same denominator SLA plus RA into Sj plus Kf plus Kb into Kt. This whole thing multiplies TL. Again one can interpret that when the load torque is there, the speed is going to be reduced than if the load torque is 0. If there is no load, the motor will run at a higher speed, so that explains this minus sign here. And of course higher the applied voltage, higher we expect the speed to be, higher the torque, the lower we expect the speed to be. So the signs look alright. Now we can consider 2 parts of omega, and as I have been doing it earlier, I talked about the response and 2 parts or even 4 parts of the response. But strictly speaking, the response that you can observe is the sum of all of them. You can't observe the individual terms separately. It is only for the purposes of study or analysis or our understanding that we look at the various parts of the response. So I will do that once again here in this case. So I will look at the part of the response that depends only on the applied voltage. So I will look at only this expression, omega equal to some multiplier multiplying EA, and therefore I can talk about a restricted transfer function from EA to omega, that is the ratio of this part of omega S to EA of S, and this will be a transfer function which will look like Kt divided by that denominator expression. So this is what may be called a partial transfer function, because it does not give you the whole of omega, it only gives you the part of omega that involves EA, the other part of omega involves TL. So this is a partial transfer function, or we say that it is the transfer function or the gain from EA to omega. It is the transfer function relating the applied voltage to the speed. What can we say about it? Well, look at it. In the denominator I have an expression in S, but you can recognize that it is a polynomial in S. What kind of polynomial? It is a polynomial of second degree, or it is a quadratic. It is a quadratic polynomial because you have 2 linear factors, SLA plus RA and Sj plus Kf multiplied together. So if I expand it out, I will get something like La into J into S squared. So it will be a quadratic. What about the numerator? The numerator is just a constant, or as one may say, a polynomial of degree 0. Therefore, now go back to what I said about transfer functions earlier. A transfer function can be associated with its poles its zeros and the gain coefficient. So, in this case, since the numerator is just a coefficient kt, what about zeros of this transfer function? It has none. There is no zero of the transfer function, the numerator is just a constant, and the associated gain may look like just kt, except that in the denominator we have something that I have to take care of. What about poles of the transfer function? Because the denominator expression is a quadratic, it has two poles, and therefore the pole 0 diagram of the transfer function will appear with only two poles, no zero, and a coefficient that multiplies the linear factors. Now, sometimes it is convenient to rewrite some of the expressions that I have been handling. For example, instead of writing SLA plus RA, I may find it convenient to pull out the factor LA, and therefore I will write it as LA into S plus RA divided by LA. This is quite correct, and of course you will see the reason for doing this. I can go one step further and write this as LA into S plus. Now, RA by LA can be written as the reciprocal of 1 LA by RA, and LA by RA is the time constant. If you remember your network theory or circuit theory courses, then in a LR series circuit there is a time constant associated with the circuit, which is given by the inductance divided by the resistance, and this time constant determines the time taken for a transient, for the current to build up to its final value or for the current to go down to its final value. As I have been saying all the time, 5 time constants or 10 time constants is just about the time required for the transient to be over. So, there is this time constant LA divided by RA, and since it is going with the armature circuit, I will denote it by tau A, and so I will have the term LA into S plus 1 by tau A. So, this is one way in which I can write that linear factor SLA plus RA. SLA plus RA can be written as LA pulled out into S plus 1 by tau A. Remember, the time constant appears in the denominator. There is another way in which this same expression can be written, and that is SLA plus RA equal to, instead of pulling out LA as a factor, I will pull out RA as a factor. So, if I do that, I will write this as RA into what? LA divided by RA into S plus 1, and therefore it is RA into tau A S plus 1. You will find in many books the transfer function terms or factors written either in the form S plus something, usually plus because that number is positive, or as I have been writing S minus Pk, where Pk is the pole, a particular pole, alternately as tau S plus 1, where tau is a time constant. One has to be familiar with both these expressions, and one expression, say S plus 1 by tau, will be useful in one application, whereas the other expression tau S plus 1 will be useful in another application, and going from one to the other is just a question of pulling out a factor and rewriting the expression, nothing really complicated. We will do the same thing with the other factor, which involves the moment of inertia and the coefficient of friction. So, I have again the term Sj plus Kf. Pulling out j, I will write it as j into 1 plus 1 divided by, and I will write down tau m, where tau m is the motor time constant, but I can also rewrite it as Kf, pulling out Kf as tau ms plus 1. So, we have these two alternate ways of writing the linear factors. One advantage of writing it this way is that the time constant appears explicitly. In one case the motor time constant, in the other case the armature time constant. Now, the next step is to look at the transfer function once again using this rewriting of the terms, and therefore I will have the partial transfer function omega divided by Ea given by Kt divided by, I have the product, and now pulling out La, I will write it as La into S plus 1 by tau A. I will also pull out j, so I will write down La into j into S plus 1 by tau A into S plus 1 by tau m, this whole thing plus kb kt. So that is how it looks. Some further manipulation is required. The idea is that I want the denominator to look like a quadratic with coefficient of s squared equal to 1. That is the way usually we like to look at a quadratic. The coefficient of s squared is reduced to 1 by pulling out a factor. It is not necessary, but it is convenient to do so, because then one can talk about poles of the transfer function rather easily. So if I do that, then I will rewrite this once again as, now what I will do is I will divide by that Laj. So I will write down kt divided by Laj in the numerator, in the denominator s plus 1 by tau a into s plus 1 by tau m plus kb into kt divided by La into j. What have we achieved by doing this? Well, let us see. In the denominator I have a quadratic. What about its roots, which are going to be the poles of the partial transfer function from the applied voltage to the speed? What about its poles? It is a quadratic, so there are two roots, and because the coefficients are all real, the two roots will be either both real and different, or coincident or repeated, or they will be complex. And in the complex case, of course, there is a possibility that the roots may be purely imaginary, or the roots will be complex and not purely imaginary. Which of the four possibilities is going to hold here? Now immediately you may not be able to figure out what is going to happen. You may have to write down the discriminant delta. Unfortunately, there is a delta that occurred earlier, that was also discriminant, but that was for the set of equations which are represented by the signal flow graph. Here this discriminant is the discriminant of the quadratic equation. One will have to look at that and consider cases as we saw earlier: delta greater than 0, delta equal to 0, delta less than 0. But one thing is immediate. I can rule out one possibility. I can rule out the possibility that the roots are purely imaginary, that is of the form plus minus j into, now here again is a clash of symbols. Usually we refer to the real part of a complex number by the symbol sigma, the imaginary part of the complex number by j omega, that is the, without the coefficient j it is omega. We use omega also to denote speed or angular velocity. So there is going to be a clash of symbols. Hopefully by context we can tell that what is what. So I am going to write here, let us say plus minus j omega k, or j omega 0 if you wish, because there is only one pair of poles for this. Is this possible? Now we saw earlier that if this happens, then the corresponding polynomial must look like s squared plus omega squared. Now is this polynomial going to look like that? What do you think? For some values of tau a, tau m, motor time constant, the armature time constant, the back EMF, the torque coefficient, the inductance and the moment of inertia, for some specific numerical values, if I substitute and simplify, will it become an expression like s squared plus omega squared? The answer is no. Why? Because if you expand out this term, the product of the two s containing terms, then the coefficient of s will be 1 by tau a plus 1 by tau m, and that is not going to become 0, because both are positive numbers. The reciprocal of the armature time constant and the reciprocal of the motor time constant, both are positive numbers. So when they add up, they are not going to add up to 0. So this quadratic will have a s term. In other words, this quadratic will look like s squared plus some coefficient, non-zero coefficient, multiplying s plus another coefficient. Not only that, this non-zero coefficient multiplying s is exactly 1 by tau a plus 1 by tau m. So it is not only non-zero, it is actually positive. So we have a situation where the coefficient of s is not 0 and the coefficient of s is positive. Now because of this, what can we say about the roots of the quadratic now? Because of this we can say that the roots of the quadratic will not be purely imaginary, that is ruled out. Will the roots be coincident? That is, will there be a repeated root? Will the roots be purely real? Will the roots be complex? They cannot be purely imaginary. Now there is one more thing that we can conclude. Now this requires a little bit of familiarity with the quadratic and the location of its roots, but as control theory people, it's good to become familiar with this. You may recall from algebra that when you have a quadratic that looks like s squared plus as plus b, then there is something that you can say about these coefficients a and b. Coefficient b is what? It's equal to the product of the two roots. So b equal to the product of the roots. And what about the coefficient a? The coefficient a is the negative sum of the roots. That is, you add the two roots and take its negative, that's equal to a, or the sum of the roots equal to minus a. In this case, the coefficient of s is 1 by tau a plus 1 by tau m. So the sum of the roots will be minus of that sum, and therefore it will be negative. So the sum of the two roots will be negative. Now from this and the fact that the product of the two roots, which is b, in this case is a positive number, so the product of the two roots is positive. From this we can draw some conclusions without actually calculating the roots. For example, if the roots are purely real, then what can happen? Can the roots be both positive? The answer is no. Why? Because if the roots were both positive, then the product will be positive, which is okay, but their sum will be positive, which is not the case. So the roots, if they are real, cannot both be positive. Can one have one positive root and one negative root? No, because in that case the product of the two roots will be negative, whereas the product of the two roots is positive, because that is the coefficient b, which in this case is a positive number. So there remains only the third possibility, that if the roots are real, then both the roots must be in the left half plane. Both the roots must be in the left half plane if they are real. I am not saying they are real, I am saying if they are real, they must be in the left half plane. Now that's good, isn't it? Because we saw earlier that left half plane poles are good. If we had a pole in the right half plane, that would have caused trouble, that would have caused something to build up to infinity as time passes. So fortunately for our motor problem, the two poles, if they are real, are both in the left half plane and strictly in the left half plane. One of them cannot be 0, because if one of them is 0, the product is 0, but the product is not 0, the product is positive. So there is no pole at the origin, the two poles are in the left half plane. This is one possibility. What about the other possibility of complex conjugate roots? That also we can consider. So if the roots are complex conjugate, can they be both in the right half plane? What about their sum then? When you add the two numbers which are conjugate, the sum is simply 2 times the real part, and therefore the sum will be positive. But we know that the sum is negative, so this is ruled out. Because I already ruled out j omega axis roots, because in that case the sum is 0, that is also ruled out. And so the only possibility is that if the roots are complex, both of them are in the left half plane, or in other words, they have their real part negative, and therefore that also gives you a good pair of poles. So fortunately for our motor transfer function, partial transfer function, from the applied voltage to the speed, the transfer function has its poles which are in the left half plane, and therefore they are good poles. Therefore we will not have any problem of omega going to infinity as time increases. Of course we do not expect it either. Nobody has seen the motor simply speeding up without any limit with a given voltage applied. It has not happened. We can now see why it cannot happen, and you will see the reason why I wrote that s factor with a multiplier, s, the multiplier pulled out, so that I could think of the quadratic as s squared plus the coefficient s into plus another coefficient. Now what about the decision between these two? Either the roots are real and negative, or the roots are complex with negative real parts. Which one of the two will hold? Now this will depend on the discriminant of the quadratic, and therefore it will depend on the relative values of the various parameters of the motor. What is the discriminant of the quadratic in this case? Delta. This is not the Mason-Gain formula delta, this is for the quadratic. Our quadratic is a squared plus as plus b, so the discriminant is simply a squared minus 4b. Our a is 1 by tau a plus 1 by tau m. Now instead of squaring it, now this is something again as engineers we ought to be doing, we ought to be simplifying expressions so that they can be handled more easily. So instead of writing a square minus 4b, well, what I am really interested is in finding out whether delta is greater than 0, in that case the roots are purely real, or delta is less than 0, in that case the roots are purely imaginary. Of course we know that delta is coincident, yes, so I have to look at the third possibility, delta equal to 0. So then I have the three conditions which I can write down. Delta equal to 0 gives a square equal to 4b or a equal to 2 root b. Delta greater than 0 gives a square greater than 4b, so taking square roots, a is greater than 2 root b, and delta less than 0 corresponds to a square less than 4b, and therefore a is less than 2 root b. So depending on which one of these relationships holds, if a, the coefficient a equals 2 times root b, then the roots will be coincident, or there will be repeated root of multiplicity 2. If a is greater than 2 root b, the roots will be purely real, of course lying in the left half plane and therefore on the negative real axis. Whereas if a is less than 2 root b, the roots will be complex but lying in the left half plane. Before actually writing any complicated expressions, let me give a numerical example to see whether there is really a possibility that any one of these conditions may occur, or is it that only one of them will occur. Now as I told you, all that depends on the actual parameter values, so in general one cannot say anything, but if you look at the form of the quadratic, is there something that one can say? So let us make an attempt. So suppose I have a quadratic that looks like s plus 2 into s plus 4, this looks like that s plus 1 by tau a into s plus 1 by tau m term plus a constant term. Now depending on what that constant term is it possible that the roots will be coincident and real, that is the case delta equal to 0, distinct and real, and distinct and complex. Now I have here s plus 2 into s plus 4, so this looks like, simplifies to s squared plus 6s plus 8, and so what should I add here so that this becomes a perfect square? Well, does not take much time to realize that if I add 1 here, then this becomes s squared plus 6s plus 1 plus 1, or s squared plus 6s plus 9, which is s plus 3 squared. So the quadratic just becomes the square of a linear factor. In other words, it has two roots which are coincident, each one is minus 3, and that is if this number which is being added is 1. So now what will happen if this number is not 1? Now it is not difficult to see that if the number is less than 1, then one thing will happen. If the number is greater than 1, then another thing will happen. If the number is less than 1, then in the discriminant a square minus 4b, the b is smaller, so a square minus 4b will be positive. So if to this I add a number less than 1, positive number less than 1, then I will get real distinct roots, whereas if I add a number greater than 1, I will get complex distinct roots, whereas if I add just 1, I will get roots which are coincident. So any one of these three possibilities could actually occur depending on the relative values of the motor and the drive parameters. So this is not just a fictitious or a waste of time to look at the various possibilities. The possibilities may actually arise depending on which one of the conditions is satisfied. A is equal to 2 root b, a is greater than 2 root b, or a is less than 2 root b. Now this can be carried out further using some additional symbols, and so I will do it only to some extent, because too much of symbolism sometimes obscures what one is thinking. Sometimes numbers are useful, sometimes symbols are useful. What is the relationship between the various parameters which will enable us to discriminate between the two situations? This is a question that one can ask. And by looking at this numerical example, I can take a hint or a cue and try to figure out. I have the quadratic which looks like s plus 1 by tau m into s plus 1 by tau a into s plus 1 by tau m plus a coefficient which is kb kt divided by la into j. Now, from this example we see that the relative value of this with the product of these two is what is going to decide what is going to happen, something of that sort. The product of these two and their sum, that determines the coefficients of s and the constant in this part. To that we are adding another constant. Now, that can make the roots coincident, or that can make the roots even complex. Now, we will be anticipating here a method which is known as the root locus method. And although we will be looking at the root locus method in connection with the use of feedback, the root locus method can be used in order to tackle this problem. Now, I am not going to explain the root locus method right now, because we have not yet introduced feedback. We have not looked at the case when feedback is introduced to improve the drive. I will discuss the root locus method at that time, but I am going to use some ideas from that method to illustrate this case. So, what I am looking at looks like s plus 1 by tau a into s plus 1 by tau m plus a coefficient which I will call k. So, I am looking at the roots of this kind of expression, a quadratic, s plus 1 by tau a into s plus 1 by tau m plus a coefficient k. Depending on the value of this coefficient k in relation to tau a and tau m, I will have one of the three situations. The root locus method enables you to find out what is exactly the case. Now, what I am looking at is the partial transfer function from the applied voltage to the speed. You remember that, and I am going to look at the poles of that transfer function. The root locus method enables us to handle this kind of a situation when you have a polynomial in which some coefficient of it can be considered to be varying, and we want to study the effect of what happens to the roots of the polynomial as this coefficient k is changed. In our case, of course, this 1 by tau a and 1 by tau m terms are fixed. In fact, all the coefficients are fixed. So, I am only saying that we want to decide which one of the three cases is holding, and that is why this whole exercise. So, for this, just anticipating what we are going to do later, and you will appreciate it when we go ahead and look at the root locus method. But the following I can say at this moment, that corresponding to these two terms 1 by tau a and 1 by tau m, I will draw it looks like a pole 0 diagram. This is not the pole 0 diagram for the transfer function that we are looking at. For the transfer function, this is the quadratic, and therefore I have to look at the roots of this quadratic whole thing. But I will draw the pole 0 diagram as it were corresponding to only this part, that is when k equal to 0. When k equal to 0, what do I have? I have two poles. One of them is minus 1 by tau a, the other is minus 1 by tau m. Now, depending on which one of them is greater than the other, their relative positions will be determined. Let us say we have a situation where minus 1 by tau a is here, minus 1 by tau m is here. So, the armature time constant pole is to the left of the motor time constant pole, or so which of the time constants is greater of the two? The motor time constant is greater than the armature time constant. Tau m is greater than tau a, therefore 1 by tau m is less than 1 by tau a, and therefore the poles are as shown. Now, if k were 0, then these would be the two poles. Now, the root locus method tells you that when k is not 0 but the k is positive, then the roots will not be these at these 2 points, but will be somewhere else. And anticipating the root locus method, what we can conclude is that as this coefficient k is increased from 0, the roots move as it were towards each other, or in other words the roots change their values till for some value of k the two roots become coincident. That is the critical value when the discriminant is equal to 0, and when this coefficient is increased further, the roots move out into the complex plane, and therefore depending on the value of this coefficient k, we will have either two real roots, two coincident roots, real roots, or two roots which are complex. So the three situations that we are looking at can indeed arise depending on the relative values of the coefficients, and one can work out the exact relationship between the relative values of the coefficients, and let me write that down and you can look at it after some simplification. So our discriminant was delta equal to a square minus 4b, where a is the coefficient of s. The coefficient of s is 1 by tau a plus 1 by tau m, so whole squared, and we are looking at delta equal to 0. So this should be equal to 4 times b. B is the constant coefficient, which is 1 by tau a into 1 by tau m plus that kb kt divided by La into j. So depending on the values of tau a, which is the ratio of armature inductance to armature resistance, tau m, which is the ratio of moment of inertia j to coefficient of friction kf, kb, which is the back EMF constant, kt, which is the torque constant, and the armature inductance and the moment of inertia itself. If this relationship is satisfied, the roots will be real. If this relation is not satisfied, but if inequality like this holds, then the roots will be real, non-coincident, and if the inequality holds this way, the roots will be complex. But in all cases we are safe because the poles of the transfer function are in the left half plane. They are all good poles. This is something we can conclude because in this case we simply have a quadratic, and so the work was easy. The root locus method enables you to draw some such conclusions when there are not just two poles, but there may be more than two poles, and there may also be zeros, that is, there may be terms in the numerator. I will tell you more about it when we come to that, but for the moment this will suffice. So we have looked at the transfer function that relates omega to Ea. Let me write it down once again. Omega divided by Ea as a transfer function was given by this messy expression kt divided by La into j in the numerator divided by s plus 1 by tau a into s plus 1 by tau m plus kb kt divided by La into j. Remember that this is only a part of the response, this is not the whole of the response, this is only the part of the response that depends on the applied voltage. Also it is a part that does not involve the initial value of the armature current and the initial value of the speed. Now can we conclude something about long term or steady state behavior from this sort of a expression or from a transfer function like this? The answer is yes. In fact, when I talked about the Laplace transformation, I mentioned a particular theorem known as the final value theorem, and one can use the final value theorem here as follows. Let us denote this transfer function by simply Gs, so that I do not have to read out the whole expression all the time. So I have omega divided by Ea equal to Gs, or I will write it as omega s equal to Gs into Ea of s. So let us now consider the special case when the applied voltage is constant. So the applied voltage, let us say Ea of t is equal to some number E, capital E, constant. So what is the Laplace transform of it? Ea of s is E by s. Therefore omega s becomes Gs into E by s. Now let us apply the final value theorem. What does the final value theorem say? That the final value of the function, that is the limit as t tends to infinity of the function, in this case omega t, equal to the limit as what happens to s? S tends to 0 of s times omega s, but s times omega s in this case, because omega s is here, is therefore limit as s tends to 0 of E into g of s, or therefore it is E into g0. So it is simply the value of the transfer function for s equal to 0 multiplied by E, that will be the final value of the speed. Once again, not the actual final value of the speed, but the part of it that depends only on the applied voltage. There is a part of it that depends on the torque. So it is as if we are only looking at the 0 torque load torque situation, or we are looking only at a part of the speed. So what does G0 become? Now if you look at the expression for G of S, this is the expression for G of S. So when I put S equal to 0, this S cancels, this S cancels, and I will get some expression remaining, and therefore it is that coefficient multiplied by E which will give me the steady state speed, or once again the part of the steady state speed that depends on the applied voltage. So let me write down that expression, and you can go back and compare it with the expression that we had earlier. So I will write it as omega steady state, I am going to write it as omega SS equal to, from what I have said just now, the applied voltage E multiplied by G0, so which is KT divided by LA into J into 1 by tau A, and I will rewrite tau A as RA by LA into 1 by tau M is KF by J plus KB KT divided by LA into J, and so getting rid of that LA into J, I will have it as E into KT divided by KB KT plus RA into KF. This is the value for the steady state speed. Check whether it tallies with the value that we had obtained earlier, that is omega SS equal to this coefficient into E minus some other coefficient into the load torque. So check whether this is the same coefficient that we got earlier. Once again, you can look at the dimensions and check whether dimensionally the two are the same. Roughly you can see it as follows: there is KT here, there is KB KT here. So if I cancel KT, I get KB in the denominator. So this looks like voltage divided by back EMF constant, but that is dimensionally speed, so it tallies. Same thing of course should hold about the other term, RA into KF divided by KT. I leave it to you to verify that dimensionally this equation is correct.